Hi, this is Professor Cummings, and this is Module 1, Lecture 5 of Lean Six Sigma. And in this particular lecture, we will be going over Chapters 6 and 7 in your Lean Six Sigma Pocket Toolbook. I mean, that's your reading. You still have to do your reading assignment. But what we're going to be doing is covering some basic questions or some basic ideas that I wanted to highlight from there, which is why we actually use statistics. Why that's such a big part of Lean Six Sigma. A major concept called the central limit theorem, measures of central tendency and measures of dispersion, representing your data visually, then going to normal and continuous data, and then finally round out with process capability. So let's start off here. We want to understand, number one, how data is actually behaving. Especially when you're doing Lean Six Sigma, it's a data-driven decision-making process for continuous improvement. How predictable is that data? In order to make those decisions, we need data that we can understand and that is indeed predictable. We want to know what is normal for the data and how much of a spread does the data have. These are all things that we need to be able to understand in order to make any type of logical decisions. Now, the person on the right of your screen that just popped up is someone named William Short. So I mentioned him earlier in this module as far as one of the people that we can credit contributing to Lean Six Sigma and how Lean Six Sigma has become important and useful in a lot of industries. Now, a lot of my examples I'm going to give are going to be based more around a manufacturing process because there's a lot of work that William Short did that gets applied to manufacturing. But this overall does apply to statistics in general and Lean Six Sigma in particular. So what did he do? Now, William Short was an engineer, a statistician, and a professor who was responsible for understanding the concept of natural variation within a process. So he was working at Bell Telephone in the early part of the 20th century, and he developed that concept that any process has a natural variation to it. So a natural variation as far as how it just varies in its particular outputs. And you could understand that using descriptive statistics. And more so, if the variation was understood, it would be possible to distinguish the chance or common causes from the assignable causes or assignable variation. So in other words, that if you knew what the process was supposed to do, if you could follow how the process was supposed to behave and understood what its natural variation was, then you would be able to distinguish when the process was going out of control. And that way you could stop any defects or stop the process before defects were even produced because you understood what that process actually looked like, what quote normal looked like for the process, statistically speaking. So again, why we actually use statistics, what it is we're supposed to get out of them. Well, statistics is the discipline that concerns the collection, organization, analysis, interpretation, and presentation of data. So that's the overall reason why we use statistics, being able to collect data and dealing with it in a systemic way. There's two types of statistics. One is known as inferential statistics, and that is a type of statistics where we look at a population, we take a sample from that population, and we make inferences about the population at large based on that sample that was drawn. Right now, then you got descriptive statistics, which is more of what we're going to be concerned with. It's used to summarize a group of data. So if you have a group of students that you want to understand their grades, that would be using descriptive statistics. So it's used to summarize graph data for a group that you choose. The process allows you to understand the specific set of observations that you're making. Going back to William Short, part of what he came and developed about understanding the natural variation of data and applying statistics to that data, particularly descriptive statistics, is the central limit theorem. And this is important because it covers really the fundamentals of what we're going to be looking at in terms of Lean Six Sigma, in terms of the statistics side of Lean Six Sigma. So if you have a population and takes sufficiently large random samples from that population with replacement, then the distribution of the samples will be approximately normally distributed. So that goes back to what the original statement was about Short. That basically if you have a population, if you have samples that come out of that population and they're done randomly, you take those observations randomly, that population will have a normal distribution. Now there are two things that go with this central limit theorem. One is the measures of central tendency, which is the idea that those observations are going to be positioned around some central value. So that was a major part of understanding its natural variation and how normal the data is. The other one is about dispersion or a spread. So it's the measures of dispersion. And this is how observations scatter from that same central value. This is where we talk about variation and standard deviation, and the central tendency, measures of central tendency, while we talk about things like mode, mean, and median. So those are always described positioning themselves around a central value. And those are three types of ways of getting a central value. And variation and standard deviations are understanding the dispersion of the data. Once you understand both of those two concepts, you can now start looking at data and understanding both where it's actually trying to go, where that central value is located, as well as how much spread you should normally expect to see in that data. So this is where we get with the idea of not only the data being normal, but being predictable. So if we look at those measures of central tendency, like I said, there's mode, mean, and median. A lot of these are things that you already understand. So mean is just the arithmetic average. So the sum of the data divided by the number of the data gives you X bar or mu, which are the averages or the means of a particular sample or a particular population. Then you got the median, which is the midpoint of the data. And again, this is an important part, ranked in order. And that is the data set tilde, X tilde. And then there's the mode, which is just the most frequently observed value in that data set. And they all serve a certain purpose because when you use them, it has to do with the data and trying to get rid of things like biases and things that may be causing an influence over your data that won't represent. So each one of these are chosen depending on how you want to represent your data and the type of data you're selecting. Then there's the ways of calculating your dispersions or the measures of dispersions. And like I said, there's standard deviation and variance. And both of these are in your book, or all of these are in your book. So the average distance from each data point to the mean. And then you've got the square of standard deviation, which is your variance, which is how far off the data values are from the mean. So what we have here, let me bring up the pen, is, there we go, up at the top, the measures of central tendency. So this is just being able to understand the data around a central value. And here are ways of understanding the spread or the dispersion of that data. So when we look at this example, here we've got an example where we've got 30 data points. It goes from 5 to 8. These are just random numbers selected. And what we can do is we can look at this data and we can start trying to apply this measures of central tendency and measures of dispersion to this data. So if we take the data and we rank it, again, from smallest to largest, 3 to 8, and we start to look for things such as the mean of that data, what we find is that the mean of those 30 data points is about 5.27, about 5.3. We look at the median and the mode. What you can see is the median here represented by the arrow is 5, and the mode is 5. It's the most common value that shows up in the data set. And based on that same data set, we can start to calculate things such as your standard deviation and variation, or variance. 1.28 and a variance of 1.65. Now let's take this data and just modify it slightly. So I took this data and I deliberately, replaced that value of 5, which is kind of anchoring the data, and just replaced it with, a few other random numbers. And what we came with is a new data set. But what I want you to look at is how the data changes in terms of its measures of central tendency and measures of dispersion. And again, this is a very contrived example, but they're just to show the influence of these numbers. So again, we got an average that's very close, 5.2. Notice that the mean and the mode separated. So the median and the mode separated. So the median is now 6, went higher, and the mode went down. The most common value in the group actually went down. So again, depending on what we're trying to understand with these measures of central tendency and looking at the data and the dispersion, forgot to put that up there, the standard deviation increased and the variance increased. So the ability to locate around or disperse from that mean, went up. So what this is telling us is, as we look at these data, or we make a decision as to which one of these measures of central tendency and measures of variance, because which one is the most important or which one is the most representative, actually starts to change. Where does the data really start to seem to locate? And which one should you choose for which application? Another thing I want you to get from this is that, this data, even though there were 30 data points and it's fairly easy to handle that amount, there's got to be a better way of dealing with statistical data. And one of those is using graphical representation of the data. And one of the ways of looking at data graphically is what's known as the box plot. So what a box plot is just a tool that gives you a visual representation. This is only one type of tool, but it gives you a visual representation that covers things such as the measure of central tendency. So you can see where the median lands. We also can find out the range or max and minimum, and we break the data up into quartiles. So the data is broken up into quartiles. So one should be able to quickly look using a box plot and be able to visualize the central tendencies, where the data wants to locate, as well as the dispersion, the spread of the data. So if we look at the data, and we consider the same information, the mean, the median, and the mode, we can capture those things right there into a box plot. And what this does is it actually allows us to be able to look at this data and see things such as the dispersion, the full dispersion of the data, the second and third quartiles represented inside this box. So this actually can technically split in half. That's the second and third quartile. And then this is the range from the max and the min. So we can see that the data has a bias just from looking at this pictorially, to the low end of our value range. And again, this is because of the influence of those particular values. And that's one of the benefits of things like a box plot and several other types of visual ways of looking at data. So now going back to what we looked at with Shewhart is the concept of normal distribution. And then this is one of the most common ways of looking at data, that's independent, randomly generated variables. And the way you're looking at normal distribution is you have the bell-shaped curve. So again, you've got the central tendency at the center of the curve, and you can see a natural spread that happens on both sides of it. So this was what Shewhart was looking at when he came up with the idea that if you took enough data points, you will start to see the natural variation that comes from its common causes and be able to pick where the special causes come in at. So this curve, you tend to see it in statistical reports, survey analysis, quality control, all sorts of different things. So it's such a normal reoccurring phenomenon. You can actually literally see this in nature. You can see this in charts for things like height, weight, measurement error, anything that can be looked at randomly and sufficiently, you can find this normal distribution. So, and that's the normal distribution, just the curve of the frequency and a measured value and how frequently you get it. And you can see that here you have a center point. Usually that's a mean. And it's called a histogram, by the way. And here you have the spread of the data. Again, you can see this in several different ways. Again, here's a look at height, men and women, and you can see the natural bell curve of both groups. Again, once you separate them, you can look at them based on their particular population. And then this is one for IQ, again showing the average IQ is 100. And then you've got a bell curve above and below that amount. Now, one of the things about a normal distribution curve is within those limits, which come out to plus or minus 3 sigma, or a total of 6 sigma, is that so much of the data is collected and can be understood to be underneath that curve, underneath the area of that curve, at 99.73%. Again, remember, this is the value that we look at when we consider, 6 sigma. The 6 sigma in our class, Lean Six Sigma, is that 99.73% of your data should fall within the bell curve of your normal distribution. So again, looking at Short and understanding, his concept, of if you have enough data, you will end up with normal distribution, and you can start to consider what are the chance causes or common causes and distinguish them from your special causes. And then we got the whole idea of a histogram and the whole idea of lean, but 3 sigma plus or minus 3 sigma, both directions. Now, if we were to take this same concept and we wanted to look at it as a continuous process, we couldn't necessarily use a histogram. So we need some sort of time function or some kind of way of distinguishing a series, but that would still apply the central limit theorem. So a concept of central tendencies, measure of central tendencies, as well as a measure of dispersion. And again, if you look at this 3 sigma, you can see that if we could chart out this data, and mind this average as well as this plus or minus 3 sigma, what we can do is we can chart out that same data, but use time or series as a way of distinguishing where this or how this data is actually performing. Meaning that these data points are now coming at you in sequence or in a series over time. And that opens up a whole new way of looking at data and a whole new way of interpreting data. So what this does is it helps us understand, concepts like control charts. So again, here's just another way of looking at this. If we have the data and we have it over time, we can start to distinguish things like what would be our common cause variation. So just random everyday events that goes on within these upper and lower control limits, as well as events that might take us outside of that, as well as things that might cause the data to not be quite as natural and random. So ended up with trends and whatnot inside of the control limits, which would still be considered an out of control condition. And that's where we come with the concept of things such as control charts and run charts. And as you can see, a lot of these things that are also considered out of control conditions, which still land within the control limits of the chart, is they just don't have the randomness that you would normally expect of having accumulated data. So we can look at these and determine them as special causes instead of common causes. And they're labeled, we don't want necessarily going through this video, but they do have names for each one of these sorts of activities in a chart. Now, there's a variety of charts You can see that the specific chart that you're looking for, whether it's a run chart or a control chart, depending on what you're concerned with, and the difference is minute with those two particular charts, but there are also charts for looking at particular errors, other types of issues that you might be able to capture in these types of time-dependent charts. So it just comes down to what your goals and your objectives are. Now, another benefit of using this type of we'll call it just a control chart, is the whole concept of the beyond the central limit theorem and the tendency to populate around a central point, as well as a measurement of dispersion, is the concept of the voice of the customer coming into this chart. So what the voice of the customer adds to it is the specification limits. So you can have the specification, upper and lower specification limits, depending on what part you're measuring and what values you have to actually achieve. These are totally independent from the upper and lower control limits, which would be considered the voice of the process. So how the process is telling you, this would be more along the lines of what Shewhart is. Bringing these together, you can start to see how well your process is satisfying what your customers' needs are. Now, this brings us into process performance, and these are metrics that are used to tell the customer how well your process is actually performing. And there are several different performance indices, CPK, PP, and PPK, and then other things that come out. But they all come down to one basic thing: is the comparison between the process's variation and the specification limits. C sub P is the difference or range in the specification over Six Sigma. There's also an upper CP, CPU, and CPL. Both of those just use half of the specification, or excuse me, half of the specification limit. So 3 sigma to the either the upper or lower specification limit. Then you have CPK, which is similar to the C sub P, but it has one difference: you're actually using the mean. So you're going more to the central limit of the process. And both of these are ways of measuring how your process is performing. So to summarize, descriptive statistics is used to summarize and graph data for a group that you choose, and this process allows you to understand a specific set of observations. If you have a population and take sufficiently large random samples from the population with replacement, then the distribution of the sample means will be approximately normally distributed. A tool used to give visual representation of observation based on median, mean, and quartiles. This is what's known as a box plot. In your normal distribution is the most common distribution function for independent randomly generated variables, and CP and CPK, commonly referred to as process capability indices, are used to define the ability of a process to produce a product that meets requirements. Okay, this is Professor Cummings. I'd like to thank you for watching this video, and hope you enjoy the rest of the course.